Hello everyone, I am Mohammad Saiful Islam. I am from 4M Lab at the University of Louisiana at Lafayette. I am working under Dr. Tanvir Faisal. Today I will be presenting my research on a multi-structural fibril reinforced poro-hyperelastic finite element model to understand the pathomechanics of articular cartilage. Here you can see 1 out of 7 between 18 to 16 4 years of old in US suffers from osteoarthritis, and 62% of them are women. Cartilage is a specialized form of firm and resilient connective tissue that can bear stress without permanent distortions. And cartilage consists of cells, extracellular matrix, pericellular matrix, fibers, and some ground substances, for example, proteoglycans. And cartilage is an avascular tissue. It means whenever it's degraded, it cannot grow itself because there is no blood cells in cartilage. And cartilage damage and disease like osteoarthritis alter the mechanical properties of cartilage. So researchers are trying to find out those like root cause of osteoarthritis and how those mechanical properties are changing experimentally. But it's hard to do it experimentally, as that you know that there are a lot of internal components of cartilage. Current techniques, even with the aid of tissue level modeling, often focuses solely on single components, neglecting their combined effects. So we proposed a physics-based multi-structural fibril reinforced model uh, using a axisymmetric finite element framework consisting of cells, ECM, PCMs, collagen type 2, and proteoglycan matrix, and to investigate the deformation behavior of dominant parameters in healthy cartilage during unconfined compression test. Now, come to the materials and methods. Here, you can see there are different layers in cartilage, for example, superficials, middles, and deep layers. And in different layers, the orientations of the chondrocytes as well as the collagen fibers are different. So when we create our geometry, we try to follow these orientations as well as the size of those chondrocytes and collagen fibers. Here you can see we also follow different layers like superficials, middle, and deep layers. And in different layers, the chondrocyte density is also different. And as we create our geometry in a like quadrant based, here you can see among the 4 of the quadrants, 3 of them have the chondrocytes. It means there is 75% of the chondrocytes cells in superficial layers. The middle layers is like 50%, and the deep layers it is like 25%. And the boundary conditions we use in our model is like in the bottoms, we make it fixed for the y-axis. In the left, we make it fixed at the x-axis. And in the right sides of the nodes, we make it the pore pressure 0. It means the fluid can flow itself very freely. From the top, we apply the unconfined compressions of up to 20% with 0.1% per second strain rate. As our models is a fibril reinforced model, we have to clear the fibers. So we clear the fibers using connector element. To apply those properties for those connector elements, we use this stress strain curve from the Shirazi et al. It's a nonlinear curve. From these stress strain curve and using the volume fractions in different layers, we calculate the force for individual fibers as well as the relative displacements. And for the non-fibril part, we use the Newton hyperelastic material, and we implemented these equations using user-defined materials. For the permeability, we use wide ratio dependent permeability equations. And if you come to the results now, these are the primary outcomes for our simulations, for our projects. If you come to the, as we stated in our research objectives, that we combined all the components of cartilage in one model. Here you can see after running the simulation, we can visualize the results for individual ECM properties, individual PCM properties, as well as the individual cell properties. We can visualize the stress distribution, deformation behavior for the like fibers also. Here you can see I showed you the bond Mises stress distribution for the superficial layer as well as the middle layer. And the maximum stress in the superficial layers and the maximum stress in the middle layers is different here, as the maximum stress is 0.416, here it is 0.379. Now come to the conclusions for our project, which is like we observe the maximum stress reductions of almost 75% of ECM to PCM in superficial zones, with further reductions observed from the top to middle to deep zones. And we also observe the chondrocytes like volumetric shifts in superficial zones, which is so much higher than their counterpart zones from medial to deep zones. We have a plan to investigate the degraded cartilage of how the mechanical properties changes from healthy to degraded cartilage. Thank you.